Hi. Welcome to our tutorial, where you will learn how to design connections, using the built-in steel connection design module in Consteel. So, let's begin. I'll continue walking you through the workflow using the simple haunched frame structure we created in the previous tutorials. The design options we'll explore are fully compliant with the Eurocode 1993-18 joint standard. Now, let's go to the Structural Members tab, where you'll find all the joint-related commands. After clicking on the Create Joint by Model button, we need to select the node where we want to define a connection. The Build New Joint Object window will open presenting several configuration options. First, we need to select the members we want in the connection to be considered. Then, we choose the connection type. In this example, we'll go with a beam-to-column configuration. By clicking on the right flange, we can specify the type of connection, depending on the forces it will need to transfer, as shown in the right-hand section of the window. Available options include in this case a welded connection, a pin simple plate, two types of moment-bearing end plate, a web fin plate and a gusset plate connection. Now, I'll choose the moment-bearing end plate connection. Let's click the Create button to start designing the joint. The Joint Details window will open, and it's divided into four main sections. The first section displays a tree structure of the joint. Here, you can view and select all components of the connection. The second section shows the properties of the selected component. The third section is the graphical window, where you can visually inspect the joint. You can use the predefined views for a better understanding of the configuration. The fourth section displays the results of the joint calculation. By default, calculations run automatically whenever changes are made, if the Automatic Calculation checkbox is selected. If this checkbox is unchecked, you can manually run the calculation by clicking the Calculation button. Let's go now to the joint loading. In this example, I'll select Model-Based Joint Loading. You'll notice that, for now, no internal forces are displayed. That's because we haven't placed the joint in the model yet. To do that, look at the bottom of the page. Next to the Documentation button, you'll find the Place button. Clicking this allows you to place the joint in multiple locations on the 3D structural model with just a few clicks, as long as the same geometry exists. Once you're done, simply click the End Joint Placement button. If analysis results are available, the internal forces will automatically be imported from the model for all the positions the joint has been placed. Let's see how we can manipulate the joint. When the column is selected in the connection tree, you can review properties specific to it, such as the section size and material grade. Setting the column's position is also important, as it influences the geometry of the joint. Stiffeners can be added by selecting stiffeners in the connection tree. You can define upper and lower web transverse stiffener plates, as well as additional flange stiffeners and shear stiffeners. Note that stiffener positions are measured from the beam's reference plan. In our example, I will define both upper and lower stiffeners. To place a stiffener, simply check the Use Stiffener box. I will also add a vertical stiffener on the column flange with a 350 mm plate length and a 500 mm distance from the reference plane. Now, in the joint loading section, all the internal forces connected to the joint can be verified since we've already placed the connection in its position within the model. Here, you can select the origin of the joint loading, either from all nodes or from specific positions where the loads are applied. You can also choose which load combinations to check in the table below, but all load combinations are calculated. When you click on an element in the table, a sketch appears below to show the interpretation of the internal forces. Moving on to the beam, here you can set the beam-related properties of the connection, such as the cross-section size and material. You can also configure the beam end, the beam span and position. You may notice a warning in the summary of results stating that the haunch web thickness is less than the beam web thickness. It does not necessarily need to be changed, but it is advisable to investigate the source of the problem. In this case, I'll check the end configuration and see that the haunch web thickness is 10 mm. While the beam's web thickness is 10.2 mm. If needed, changes can be made to the sections in the joint module. For example, I will now change the cross-section of the beam to an IP 550. Note that changes made in the joint module affect only the joint calculation, not the 3D model. When closing the joint module, you will see some yellow bullet points in the Diagnostics panel with possible errors, indicating that the joint model and the structural model are different and that the joint model must be updated. At this stage, there are two options. Change the section in the structural model, or select the joint here and update it using the button below. This button updates the joint model so that it matches the structural model. To open a previously saved joint, we can use the Edit Joint function. We left off at the end plate properties. The geometry and material can be edited. We will leave the width and height as they are, but change the thickness to 25 mm. Let's also modify the bolt parameters. By clicking the Modify button, a new panel will open with more options related to the bolt type. In this example, we're using the standard EN 14399-3. I'll change the bolt size to M24 and the material grade to 8.8. We'll use washers on both the nut and the bolt head. The information related to the bolt, nut, and washer can be viewed on the right side of this window. In the end, press OK. Now let's verify the position of the bolts. We will need 4 rows. For the pitch of the holes, set E1 to 70 mm, P1 to 360 mm, P2 to 140 mm, and P3 to 500 mm. The position of the end plate can remain at -5 mm. An error message appeared indicating that the distance between the bolts and the column web is not sufficient. Let's solve this by changing the edge distance to 45 mm. The last thing we need to look at is the welds. If automatic weld optimization is turned on, we only need to select the method for weld design. If we turn it off, we can manually set the weld dimensions for all positions. If there are no more errors or warning messages on the right side of the screen, and we are satisfied with the results, we can click OK to save the connection. Let's create a ridge rafter connection in the same manner with the Create Joint by Model function. I will select the position and moment end plate connection type. I will now place the connection in the 3D model to get preliminary results. I can see that the moment utilization is higher than allowed in both the right and left beams. To address this, I'll go directly to the end plate settings, either the left or right beam, it doesn't matter, and enable the equal end plate option at the bottom of the page. This way, we won't need to repeat the modifications for both plates separately. Then I will modify the bolt standard, set the size to M24, and change the material grade to 8.8. An error message indicates that the distance between the bolts is insufficient, so I will adjust it as well. I'll set the bolt layout to 3 rows, with the distances between them as follows: 70 mm, 300 mm, 80 mm, and 70 mm. I will press OK to save the connection. Now, let's create the final connection type using the Create Joint by Model function again. This time, I'll select a pinned base connection type. Instead of placing the base plate the way we did previously, I will simply rename the joint to pinned base and close the joint details window by pressing OK. Then, close the joint window as well. Next, open the Place Joint function. Here, we need to identify the joint we want to place, and by pressing the Place button, we can set all the required positions in the model. When we finish the positioning, simply close the window by clicking the X in the corner. You'll now see a green symbol indicating where the joint was placed. To make it easier to identify the placed joint, we can turn on the names and positions of the joints. To do this, go to the Visibility settings and enable the Joint Model Names option. This joint can also be selected directly from the 3D model interface. If we go to the Object Properties window, we can see the selected placed joint. By clicking the 3-dot button next to its name, the same Joint Details window will open, where we can continue and finish the design of the connection. Now, for instance, if we go to the joint loading, it will be easier to identify the origin of the joint loading in the model with the names turned on. Let's make some modifications to the base plate, as the connection is currently slightly overdimensioned. Instead of using 2 bolt rows, we'll reduce it to just 1. We'll also change the end plate height to 440 mm, and update the end plate position to -20 mm. Save these modifications by clicking OK. Now, let's see how we can include the connection stiffness in the global analysis. To do this, go to the Analysis tab and review the first-order calculation results. Select Load Combination 5 and focus on the internal force My, bending moment in the Y direction. Switch the view to front view, and use the slider to slightly increase the diagram scale. For example, observe the right rafter. At its right end, the bending moment is 616.43 kN, and at the left end, it is minus 255.12 kN. To include the connection stiffness in the analysis, go to Analysis Parameters and, under Global Settings, enable the Include Connection Stiffness option. After rerunning the calculation, you'll notice that the moment at the right end slightly decreases to 601.81 kN, while the absolute value at the left end increases to minus 274.28 kN. After rerunning the analysis, it is recommended to check again the internal force My connections to see how the utilization changed with the newly obtained analysis results. For instance, in our example, the column-to-beam connection is perfectly fine, but the ridge rafter connection needs some reinforcement. I will change the end plate thickness for both sides to 25 mm. The base connection is fine as it is, so we can save it without any modifications. That was our guide for the connection design in Consteel. Thanks for watching. Click the like button if you would like to watch more similar videos, and don't forget to subscribe.